ఇది ఉంది కదా ఇది పెట్టేశాను. Okay, in the first session, that was last session, we talked about why quantum computing, what is quantum computing, why quantum computing, then what is formal definition of qubit, next what does superposition mean, then what does measurement mean. These are the things we discussed, okay? And so what is general form of qubit? Qubit is represented as alpha ket 0 plus beta ket 1, okay? Where alpha, beta are complex numbers. Ket 0 is 1, 0, ket 1 is 0, 1. And what is the condition it has to satisfy? Mod alpha square plus mod beta square is 1, 1, 1. Okay? Okay. So whenever we say qubit means that to quantum system, it has how many possible classical states? 2. Okay, now then only we call it as a qubit. Okay. Now if I go for, is it a qubit or not? Please. Is it a qubit state or not? Yes, it is a qubit state. So now if I go for measurement, the same thing I can write it as, now you are familiar with the notation. Directly we can write it as like this. Is that okay? Ket psi is called something like this. Now if I go for measurement, what is the probability of getting 0 state? 1 by 3. What is the probability of getting state 1? 2 by 3. Total probability is 1. Okay, only that much only we discussed so far. Correct? No? Okay. So now this is a basis for two-dimensional space. This is a basis for two-dimensional space. Okay. Now similarly, you can give basis for 4-dimensional, 5-dimensional, 6-dimensional. At least one basis we should be able to give. Okay. All of us know what is a matrix. We know what is a square matrix. Let us say this is, I am performing an operation. An input to this operation is 0, 1. When 0 is input, okay, that is continue. Okay, so I am performing an operation. That operation, that what does it do is, if 0 is given as input, it changes it to 1. If 1 is given as input, it changes to 0. Now in this case, if I tell you what is output, is it possible to uniquely determine what was the corresponding input? In this case, input outputs are mapped like this. Okay, no? That means, is it possible to reverse this operation? Yes. That means if I give output, you are able to uniquely determine what was the corresponding input, no? That type of operation, we call it as a reversible operation. Now this operation is reversible. Now let us take one more operation. Let us say PQ. These are the inputs. Output is say something like this, P and Q. Now tell me, is it reversible operation or not? No. Why? If it is output is 1, I am able to uniquely map to the corresponding input. If output is 0, we are not able to uniquely map to the corresponding input. So that means, is it reversible operation or not? Not reversible operation. This operation is reversible. So let me give you one more. Okay. In this case, is it reversible operation or non-reversible operation? That means what? What does it mean? There must be one-to-one mapping between inputs and output. For every output, there must be unique input for which it is mapped with. Is that okay? Now you tell me finally, is it reversible or not reversible? Reversible operation. 1 and 3 are reversible operations. Okay. Now can you give another example for an example for non-reversible operation? R operation. Okay, no. So P, Q, and already given here, P, Q, these are inputs, P or Q. Okay, no, P or Q. This is a output. 0, 0, 0, 1, 1, 0, 1, 1, 0, 0, it is 0, 1, 1, 1. In this case, again, from output, it is not possible to determine uniquely what is the corresponding input. This kind of operation, we call it as non-reversible. Now, 2 and 4 are non-reversible. 1 and 3 are reversible. Now, what is our observation? In case of reversible, what is happening? Number of inputs. How many inputs are there? Same outputs. No. That means here one input, one output. But here, 2 inputs, 2 outputs match. But here, if you see, 2 inputs, 1 output problem. That means it is not of that. Here, 2 inputs, output. Then that is not a non-reversible operation. All quantum operations are reversible and they are represented by some kinds of matrices. Okay? Some types of matrices. That matrix is, now is it clear what is reversible operation? Okay. Now, that's all, bijection, one-to-one mapping. Correct, madam. Control L. Okay. Okay. Okay, anyhow, we okay. So last session, here in this session, we are going to see some quantum operations and some circuits based on that. After that, depending on the availability of time, and okay, now we will see other things. So quickly, we review. This is formal definition of qubit. Okay. Now, are these qubits or not? Qubits. This is not a qubit. Why? Because mod alpha square plus mod beta square is not equals to 1. Qubit means that is a linear combination. This linear combination only we call it as superposition state. Okay, these are the examples. Measuring means we know. So after measuring, we will get one of the classical states as output. And each classical state, there is a probability associated with it. What is the probability with which we get that classical state? In this case, what is the probability of getting 0? 1 is also 1 by 2. Total probability is 1. In this case, what is the probability of getting 0? 8 by 9. Probability of getting 1? 1 by 9. Total probability is 1. Okay, similarly, other examples. Okay. Okay. In this case, what is the probability of getting 5 when I go for measurement? 2 by 9. 2 by 9. Now measurements clear? No, measurements and definition. Now this already we discussed what is reversible operation. Now this not operation is reversible or not? Reversible. Whether this operation is reversible or not? Not reversible. What about this operation? Yes. So observation is, okay, this operation name is C naught. Later we will discuss why it is C naught. And operation is not reversible. Observation is, if they are reversible, they have equal number of inputs and outputs. Next, all quantum operations are reversible and they are represented by some special kind of matrices. So to understand that, we should know what is conjugate transpose of a matrix. Morning also we discussed, no? Given a matrix, we can find transpose. After that, conjugate all the elements. What is conjugate of A plus IB? Complex conjugate of A plus IB? A minus IB. Now, can you tell me what is complex conjugate transpose of this matrix? 1 minus I, 3 minus 2I, 2 plus I, and 4. Okay? This, if B is a matrix, its conjugate transpose is given by B dagger. That notation is dagger symbol. B dagger. Is it okay? What is conjugate transpose? Transpose and take a conjugate of all the elements. If it is a real number, conjugate is same as that number only. Is that okay? Okay. Now all quantum operations are represented by special matrices called unitary matrices. When do you say that a square matrix is unitary? U is unitary if U times U dagger. Now we know what is U dagger. What is U dagger? Conjugate transpose of U is equals to U dagger times U equals to identity. Then we say that that square matrix is unitary. That means it represents some valid quantum operation. So finally, quantum operation means what? It is one matrix. No, it is represented by one matrix only. But that matrix should have some special property. That's all. Okay. Now you tell me, is it a unitary matrix or not? All of you, can you try? Because that is identity matrix. So its transpose is again identity. All are real numbers. All are real numbers. Hence, conjugate transpose is same as transpose. 1001 is same as 1001. If you multiply both, again 1001 only we get now. Okay? Okay. So 1001 is unitary matrix. No, it is not changing. Okay, that's what we discussed. Similarly, the other side also it is true. Hence, 1001 is unitary matrix. That means it represents a valid quantum operation, some quantum operation. Similarly, 0 minus I0. Can you check 0 minus I0? Okay, we will discuss. 0 minus I0. What is its conjugate transpose? What is its transpose? Transpose is 0I. First row is 0I. Second row is 0I minus I0. This is its given matrix transpose. What is conjugate transpose? 0 no change, 0 no change. This I becomes minus I. This minus I becomes plus I. That means it is same as original matrix. Okay. This is only coincidence. Okay, no. Multiply, then after multiplying, we are getting identity matrix. Similarly, the other side also identity matrix. Hence, this is a valid quantum operation. 0 minus I0 is a valid quantum operation. Is that okay? Okay. Now, is it unitary? What is e power I theta formula? Cos theta plus I sin theta. Cos pi by 4 is 1 by root 2. Sin pi by 4 is also 1 by root 2. If you substitute, again same procedure is same. You can see that this is also unitary matrix. Okay. If I change instead of pi by 4, pi by 2, I'll get another matrix. That is also unitary. Not only for pi by 4. In general, e power I theta, that is unitary. Theta is anything, it is unitary. By changing theta, then we will get different, how many matrices we want, that many matrices. No, all are quantum operations, valid quantum operations. Now we have infinite number of quantum operations, no, by changing theta value. Is that okay? Again, okay, maximum 360. At least you can assume 360. But if I take real numbers, infinite, no? Are you okay? Now, each operation, the other name is gate. We use gate and operation interchangeably. So, if this is the matrix, then for this there is some name that is called X gate or X operation. This is also 0, 1, 1, 0. You can check. Again, this is unitary matrix. This we have already checked. This is also unitary matrix. That means it is some valid quantum operation. This is also one valid quantum operation. This is also one valid quantum operation. All are quantum operations. Like this, there are thousands of operations. These are different quantum operations. But all the matrices whichever I have shown here, how many rows they have? How many columns? 2 by 2. That means they work on quantum systems where number of classical states are 2. That means what? That means what? Thank you. That means qubits. Single qubit they work on. All these quantum operations input is 1 qubit. Why? 2 rows and 2 possible states. No, 2 rows and 2 columns. Okay, like this. These are different operations. Okay. Now we will see one. At least we try to understand some basic operations. Okay. Once you understand some operations, now after that every operation is same. Only matrix changes. Procedure is same. No, ditto. Same procedure. Okay. Classically we have NOT gate. What is that? 0 to 1, 1 to 0. Here also quantum NOT gate we have. Okay. So that matrix is given by this 0, 1, 1, 0. This acts as NOT gate, but in the quantum sense. What is that it is expected? Classical 0 to 1, 1 to 0. Here what should do? Ket 0 to ket 1, ket 1 to ket 0. But quantum means not only these 2 inputs, no. We have so many other inputs. Are you... See, classically we have NOT gate. Its counterpart in quantum is X gate. It is represented by matrix 0, 1, 1, 0. 0, 1, 1, 0 is unitary matrix. That's why it is a valid quantum operation. Valid quantum operation. Now, how to represent the X gate? Any gate we need to say what is input, and that gate name, this is the standard notation it is used, a box and the name of the gate. That's all. X gate they represent like this. Is that okay? Now, if I give input here, 0, ket 0 is input. Then what is, this is called measurement symbol, meter symbol, measurement symbol. So now we have ket 0, this is input. This input we are giving to X gate, and here we will get some quantum state. This state we are measuring, then we will get some output. Okay, let us call this is T0 state, T1 state, and here some output. This is classical output. Output is always classical. Is that okay? Okay. Now, what is the state of this at X here? Ket 0 only. At T0, the state is ket 0. What is the state at T1? It is X gate we need to apply to this input, no? Which is X gate I need to apply to input. What is our input? Ket 0. X on ket 0. What is X on ket 0? X is 0, 1, 1, 0. What is ket 0? 1, 0. If you multiply, we will get 0, 1. What is 0, 1? Ket 1. Is that okay? 0 is input, ket 0 is input, X on ket 0, X on ket 0. X means this is the matrix. This is the matrix. 0, 1, 1, 0 is the matrix. Ket 0 is 1, 0. X if you, this is normal matrix multiplication. This is normal matrix multiplication that we have already done. Okay. So we'll get 0, 1. 0, 1 means ket 1. Okay. So here answer is ket 1. So similarly, instead of 0, if it is 1, okay. If it is 1, so now here the state is what? Ket 0. So ket 0 we can write it as 1 times ket 0 plus 0 times ket 1. Now if I go for measurement, what is the probability of getting 0 here? 1. That means always answer is 0, no? Sorry. Thank you, madam. Okay. This is ket 0, no? Answer is 1. So 1 we can write it, a ket 1 we can write it this way. That means if I go for measurement, always we get state 1, second state as our answer. Is that ket 1 we can also write it as 0 times ket 0 plus 1 times ket 1. Linear combination. Ket 1 is 0, 1. 0, 1 I can write it as 0, 0 plus 0, 1, no sir. This 0, 0 I can write it as 0 into 0, 0 into 1, 0 plus 0, 1. 1 into 0, 1. 1, 0 is ket 0. 0, 1 is ket 1. That's what I have written here. Okay. Okay. That means if I go for measurement of ket 1, what is the answer we get? Always 1. Okay, now can you try with 1? What is the answer we get? Okay, let me change here. All of you try. Okay, now please try and tell me. So what is the state here? Ket 1. At this point, T0, ket. What is the state here? X gate I need to apply to ket 1. What is X gate? 1, 0. What is ket 1? 0, 1. Multiply this, we will get 1, 0. That means what is the state here? So ket 0 we can write it as 1 into ket 0 plus 0 into ket 1. That means if I go for measurement, what is that we get? Always 0. 1 we never get. Is that okay? Why? Because total probability is 1. Okay, now you can see this. If you have any doubt, to ask me. Is that okay? Same thing. Okay. Is there any doubt in this? Okay. Only matrix multiplication, if you understand, that is enough. Only 0, 1, 1, 0 we need to remember, that is no other option. If it is open book test, we need not remember that also. Only matrix multiplication is required, that's all, no. Okay. Now, is it possible to give any other thing other than 0, 1 as input? Yes is correct answer. Why? In classically only 0, 1 are the possible states, but here qubit means alpha ket 0 plus beta ket 1. 1 by root 2 ket 0 plus 1 by root 2 ket 1 you can give. Not only that, any alpha ket 0 plus beta ket 1 we can give, no? With mod alpha square plus mod beta square is that guarantee. That means infinite inputs are possible here, no? Not only ket 0, these are special cases, that's all. Okay, now let us see what happens if I give alpha ket 0 plus beta ket 1 as input. That is, my state is like this. Here I am giving alpha ket 0 plus beta ket 1 is input, where mod alpha square plus mod beta square is 1. If this state is given as input, you follow the same procedure. You try, okay, no, 1 minute. You please try. How to write it in matrix form? This is direct notation, no. This is direct notation. How to write it in matrix form? Okay. So alpha, okay, here I am writing down. Alpha ket 0 plus beta ket 1 is, alpha ket 0 is 1 0 plus beta ket 1 is 0 1, which is same as alpha beta, no? So it is nothing but you are given alpha beta. Now can you try? What is that we need to do at T0? What is our state? Alpha ket 0 plus beta ket 1. What is state at T1? Thank you very much, sir. Alpha 1, beta 0. How did we get that? So here T1, what is state at T1? X gate we need to apply to alpha ket 0 plus beta ket 1. Okay. No. Final answer. What is X? 0 1 1 0. What is matrix form of this? This I have written in matrix form. This also I write in alpha beta. If we multiply, we will get beta alpha. Again, bring it back into direct notation. Beta ket 0 plus alpha ket 1. What is observation? Alpha beta got interchanged. That's all, no. So general qubit also we can apply X gate. In that case, what happens is alpha beta gets interchanged. That's why this 1 and 0 are special cases. See, 0 and 1 are interchanged when we apply X gate. That's why X gate on 1, ket 1, it is becoming ket 0. X gate on ket 0, it is becoming ket 1. Are you? Okay, another way is by linearity. What is that? See, given state is ket psi, alpha ket 0 plus beta ket 1. So we are writing x of ket psi. X of what is psi? Alpha ket 0 plus beta ket 1. By linearity, what is that we can do? Alpha is a constant. Alpha times x on ket 0 plus beta times x on ket 1. Is that okay? What is x on ket 0? Already we calculated, no? Ket 1, ket 1. What is x on ket 1? Ket 0. Is that okay? Now you substitute back those values. Alpha ket 1 plus beta ket 0. Same thing, no? Either that method or this method, answer is same, no? Finally, our observation is amplitudes of ket 0 and ket 1 are interchanged. That's all. Okay, now this is our final state. Okay. So some examples quickly. Swap the coefficients of ket 0 and ket 1. They are called probability amplitudes. Now what is answer? What is answer for this? X on this. Sir, 0 times correct. Only thing is this 0 you put here, this 1 here. 0 times ket 0 plus 1 times ket 1. Is that okay? 0 times ket 0 plus 1 times ket 1, which is same as ket 1. What is this? This is nothing but ket 0. X on ket 0 is ket 1. Same thing we got, no? Okay. 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 Ket1. How to write Ket1 in direct notation? Alpha Ket0, this form. Is that okay? Now apply X gate on Ket1. Apply X gate on Ket1. What is our answer? 0 and 1, they are interchanged. So we'll get this, which is same as Ket0, correct? No? Now you tell me what is answer for this? 1 by root 2 Ket0 plus 1 by root 2 Ket1. That means same thing is the answer. What is answer in this case? Yes, sir, that's all. But still, it is addition only, no, sir, it doesn't matter. That's why I have written that. Okay. In this case, what is answer? 1 by 3 Ket0 plus 2 plus 2i by 3 Ket1. That's all. No, clear? No, in general, any alpha Ket0, beta Ket1, alpha, beta, we need to interchange. Is that okay? X gate, any doubt? 0, 1, 1, 0 is the matrix. Ket0, what happens? Ket1, what happens? Alpha Ket0 plus beta Ket1, what happens? Okay? Which one, madam? Sorry, this is typing mistake, madam. That I will correct it, okay? Thank you for pointing it out. Okay? That I will correct. Okay, no, sorry. Okay? Okay, this is one quantum operation. Like this, we can talk about many quantum operations. First, let me explain other things, then again we'll come back to different examples. Next, simple quantum circuits. Okay? Oh, correct. Thank you. ఇక్కడ రాసేదానికి అటైనా ఒకటి మీ ఇష్టం. ఓకే, బ్రేకప్. Because hybrid means for them, it here advantage is more, no, sir, physically. Okay. So we know what is a resistor. What is a resistor? Collection. Okay. It is for storing collection of bits, no? If I say 8-bit resistor means we can store 8 bits of classical information. Similarly, we can talk about quantum resistor. What is that? It can store, it should be able to store qubits. N qubit resistor means it should be able to store n qubits of information. Okay. So initially all quantum bits, no, they are qubits are assumed to be in 0 state. Okay. Okay. Same analogous to classical. Here it is quantum. There bits. Here qubits. N qubit resistor. There it is n bit resistor. Okay. Now, the logic circuit we know. No. Okay, we have some logical gates. Some input state will be there. We apply some logical gates. Again, we'll get some output state. Here also, instead of that, the gates are going to be quantum gates. That's all. So input state will be quantum state. We apply some quantum operations. Again, we will get some output. Okay. Now we know at least what are quantum gates or quantum operations. They are represented by unitary matrices. That means finally on the input state we apply some matrices and do multiplication. That's all, no? Inside whatever we are doing, if I say all are quantum operations, I am only applying some matrices are there. We need to do some multiplication. Is that okay? Okay. So this is input. We apply some quantum operations or gates, some sequence of gates. Then after that, here we will get quantum state. But this quantum state we cannot do. We don't know what is the actual information stored in that state. If you really want to know what is the extract the information, we should go for measurement. Then we will get the classical output either 0 or 1 here, 0 or 1 here, 0 or 1 here, 0 or 1 here. This is the procedure, no? Okay. Now we will see what. Okay. This is. Can you consider it as an example for quantum circuit? So input is this. Here some gate. That name also that we will leave it. Okay, this is some gate, some gate, some gate. This is measurement. Okay, na? This H stands for some hard mod gate. Some of you, those we have That anyhow we'll discuss. Okay. So now I said yes, X is a gate. Now I need to clearly say which this is also similar to X. It is also single qubit gate. That means what? It needs 1 qubit as input. In classical, NOT is a single qubit, a single bit gate. No, NOT gate is classical. NOT gate is single bit gate. That means it requires either 0 as input or 1 as input. 1 bit of information. Here it is single qubit gate. 1 qubit is input to this, similar to X gate. That means alpha ket 0 plus beta ket 1. Then I need to say what is the corresponding matrix for this H. So the corresponding matrix is 1 by root 2, 1 by root 2, like this. All 1 by root 2, last minus 1 by root 2. Is that okay? There it was 0, 1, 1, 0. Now only matrix is different. No. Only matrix is different. Is that okay? Okay. Now, can you please calculate now? This is the circuit diagram for that general diagram. Wherever X is there, we replace it with H. That is only standard notation. If there is Y, H is replaced with Y, Z, H is replaced with Z. It goes S, replaced with H. Same style. Now, can you find out what is the answer for this? So here it is ket 0. Ket 0, what is the answer? What is the answer? This is H gate. What is answer? What is state at T0? Ket 0. What is state at T1? Hermite gate we need to apply. Hermite gate to ket 0. This is our input state. No. Same procedure. Whether it is H or X, same procedure. Even if I give some other matrix, again same procedure. Once you know matrix, you should be able to apply. Okay. What is H on ket 0? What is H? 1 by root 2, 1 by root 2, 1 by root 2, minus 1 by root 2. What is ket 0? 1, 0. You multiply both. That's all. This is the output. This is matrix form. What is Dirac notation? Ket 1. That's all. This is the input output. That means the state here is this much. Is that okay? Okay, na? This is known as plus state. This is known as plus state. Okay. Ket plus. Ket plus. Now you remember this matrix 1 by root 2, 1 by root 2, no? Okay. Now can you try for 1 here? What is the answer? You please tell me. 1 by root 2 minus 1 by root 2. 1 by root 2 minus 1 by root 2. Now if I go for measurement, what is the probability of getting 0? 1 by 2. What is the probability of getting 1? 1 by 2. Correct, no? So this is called equal superposition state. Both have same probability of occurrence. Okay, no? If I go for measurement, both have same probability of occurrence. This is called equal superposition state. Okay? Okay. Now similarly do for 1. This is the answer for 1. This state is called minus state. Now this 1 by root 2 minus 1 by root 2. I said no, this is also basis. 1 by root 2, 1 by root 2, comma 1 by root 2. That means ket plus ket minus is also basis. What is ket plus? 1 by root 2, 1 by root 2. Ket minus is root 2 minus 1 by root 2. This is also basis. Morning I mentioned, no, for 2 dimensions, 2 different bases. 1, 0, 0, 1 is not only the basis, there are other bases also. 1 by root 2, 1 by root 2, comma 1 by root 2 minus 1 by root. This basis is called Hermite basis. Hermite basis. Okay? So later you will understand in future, depending on the type of basis we are using for measurement, answers will change. Now whatever I am explaining is, it is standard basis measurement. 1001 basis. That is called standard basis. Same question, if I say that I am doing measurements in Hermite basis, answer will change. Okay, that slowly you will understand that all these things. Okay. Now here also, this is also equal superposition state or not? Whatever be the probability of getting 0, same thing is the probability of getting 1. Same thing is the probability. Why? Because my mod minus 1 by root 2 is again 1 by 2 only, no? Whole square. Okay. Okay. Now let us determine output of this quantum circuit. Quantum circuit, simple quantum circuit. Okay, you try. I don't explain anything. Time is from left to right. You apply your wisdom and try to find some answer. If it is wrong, also fine. Later you will understand. No, what is that? What is the correct way, or how you are not supposed to do? Same order. First to apply H gate. Whatever answer you get, apply X gate. That's all, simple. That's all. That's all. No. Is that okay? So first, ket 0 is input. Apply Harmar gate. Okay. So we have taken like this. This is simple circuit. Our general procedure also same. T0, what is the state? You write down, it is same as given state. What is state at T1? No, don't give me state. You express in terms of gate. H on ket 0. If the, okay, whatever answer, leave it. Because if I change the input gate, answer changes. Now general procedure we are trying to understand. Are you? H on ket 0 is the answer we get at T1. What is answer at T2? X gate we need to apply to this answer, whatever answer we get here. Is that okay? Is that okay? Okay, this anyhow we know that. What is H on ket 0? We have already. Okay, this we know that. Now, what is the state at T1? This is the state at T1. If you want direct notation, this is the state. Now you apply which gate we need to apply? T2? X gate. X gate to this. What happens? We have, okay, no, these coefficients are swapped. Okay, every time we need not do, now we know that no, they are swapped. Answer is same thing. Measurement gives 1 by 2, 1 by 2 with equal probability. Now you interchange X and H and find out answer. Swap. Wherever H is there, you put X. Wherever X, then at least we will know. Changing the order of the quantum gates, whether it results in same answer or different answer. If you get one different answer, gone. Then we can say that ordering is very, very important. Okay. Okay, 1 minute, you give it a try. So what's the answer? Oh, okay. దీనికే అంతే సార్, అంతే 1/√2 get 0 minus 1/√2 get 1. That's all. That's all. Simple, no? See, already we have what is state at T1? State at T0 get 0. State at T1? Okay. Okay, state at T1 is x on ket 0. What is x on ket 0? 0, 1, 1, 0. Anyhow, we know that, no? Ket 1. So it is ket 1. Ket 1. Now what is state at T2? X on ket 1, sorry, h on ket 1. This also we have already calculated. Directly you can write 1/√2 ket 0 minus 1/√2 ket 1. That's all. Okay, no? So that means ordering has given different answers, no? So from this conclusion is ordering of the gates is important. Okay, no, that is important. Okay. Now, if I give 1 here, okay. So instead of that, if I give 1/√2 ket 0 plus 1/√2 ket 1, you keep doing from starting, no? Some answer. But that means again you are applying X gate, again you are applying H gate. Here 2 gates, okay. If our circuit contains 100 gates, again from starting you need to do 100 times. That I will tell correct only. So that we don't want to do it that way. That is our intention. If 2 gates means simply we are able to do and correct immediately before I complete question, you are able to give answer, no? Okay. But if 100 means it takes time. It does not mean that not possible, but it is only lengthy process. Okay. Now, if at all we are able to find this entire circuit, so we know that this is quantum state, this is our entire block diagram, there are many gates. For this corresponding to all these gates, if I find only one matrix corresponding to all the gates whatever you have used, then what becomes easy? Here this is output, this is input quantum state, this is output quantum state. Okay. Then if you change input, I need not do it every time. Only this matrix directly I'll apply. Only one matrix we apply. Then job is easier, no? What is the difficulty? Is it? See, this method for the different input every time we need to do from scratch. That means first stage, second stage, third stage. Same thing we need to repeat by changing the input. Now, is it possible to do it only once and use that? Okay, in this case, what is that we can do? So first which gate we are applying? X. Okay, this anyhow. We are applying X gate. After that, what is the next gate? H gate. Because our input is going to be here, no? Input is here. First gate applied is this one. Second gate applied is this one. That's why this order is correct, no? Is that okay? Now, find out H into X. H is a matrix. X is a matrix. Find out H into X. That is only matrix multiplication. That gives you single unitary matrix corresponding to all gates, 2 gates. We have this entire box unitary matrix we get. One operation only, sir. But here, if I go by this method, 2 times I need to do. Instead of this, then directly I'll get one matrix. Second one. This is second PPT, no? Second one only. Okay. I'll change it. Okay, I'll change it. Okay, I'll try.
దీని నుంచి అంటే దీని మీద ఓవర్ రైట్ చేద్దామా సార్, లేకపోతే notepad ఏదన్నా ఓపెన్ చేద్దాం సార్.
Here only this PPT is there no already.
Yes,
No
sir.
problem. I can write this online class type. Now for you, it will let us try 1 minute. If it works, okay. Otherwise, we will go with our golden method.
దీని మీద అవటం లేదు. దీని మీద అవటం లేదు కానీ పెయింట్
వస్తుంది ఏంటండి 1 second. It works. I know that. Draw. It is working, no?
Yes, sir.
But
Full screen, sir. ఒక్క నిమిషం. ఒకసారి వదిలేయండి సార్. సార్ వీడియో కనిపిస్తుంది. ప్రింట్ చేశారా?
అది అనిపించేసి పెట్టుకున్నాను.
Okay. Anyhow, you can complete that. No, meanwhile, completed. So, what's the matrix? H into X. 1 by root 2 minus 1 by root 2. Now X is there. No, 0, 1, 1, 0. Multiply. Okay. Next. It is not changing. Okay. Let us see. No, but it is not moving. No.
ఏదైనా సరే వాడుతున్నాం. ఇంకొక
ఇదే మనకి ఇది ఇంపార్టెంట్ అంటే ప్రతి దానికి పాస్ పెట్టాను నేను. Okay, I will try to minimize writing.
పెయింట్ ఓపెన్ చేయమంటారా సార్?
అయితే ఈ పీపీటీ మాట్లాడగలరు. ఓహో, లేకపోతే
సార్ చూడండి సార్, మళ్ళీ ఒకసారి try చేయండి.
ఇదేంది అసలు పోవడం లేదు.
ఇది దాని ఊడిందేమో సార్. ఒక్క నిమిషం.
కంట్రోల్ ఎల్ కొట్టండి.
కంట్రోల్ ఎల్ కొట్టలేదు సార్.
కంట్రోల్ ఫుల్ స్క్రీన్. Now it is working, but
మీరు రాయలేరు.
ఓహో, అటైతే మినిమైజ్ చేసి రాయాలి.
లో రాయలేము సార్.
ఓహో, ఓకే.
ఎపిక్ పెన్ అని ఒకటి ఉంటుంది సార్, అది ఇన్స్టాల్ చేసేద్దాం సార్.
ఏమో నాకు తెలియదు మరి. ఓకే. However you want me to proceed, I can proceed.
ఓకే. ఇప్పుడు పెయింట్ యూస్ చేసి పెయింట్ రాసిన తర్వాత మళ్ళీ నెక్స్ట్ ఈ విండోకి షిఫ్ట్ అయితే సార్.
ఏమో మరి వాళ్ళ కన్వీనియంట్ అయితే ఓకే, నాకేం ప్రాబ్లం. ఎంతమంది ఉంటారు ఆన్లైన్లో? ఎంతమంది ఉంటారు?
రికార్డింగ్ పర్పస్.
ఓహో, అది మెయిన్ ఇంటెన్షన్ కదా.
పెయింట్ యూస్ చేసి 2 టాబ్స్ గా షిఫ్ట్ అయితే
మీరు ఎలా చేయమంటే అలా నాకేం ప్రాబ్లం లేదు. మీరు ఏది చేయమంటే అది చెప్పండి, నాకేం చేయాలి అంతే చాలు. ఎక్కడైనా పెయింట్ పెట్టండి, అది మనకి కనీసం అలవాటు. ఇది కూడా రికార్డ్ అవుతుందేమో. పెయింట్ పెట్టండి సరిపోతుంది. Okay, so now if we find H into X, we will get single matrix. You check whether it is unitary or not. Whatever matrix you got, is it unitary matrix or not? Yes. Anyhow, that well-known result, product of unitary matrices is unitary. Unless you make mistake, you should get same correct answer. That is unitary. Now we have got U. Okay, we have got U. You use that U. By using that U, you apply input ket 0. U on ket 0. U is known now. Ket 0 is 1, 0. One by root 2. This input 1 by root 2 minus 1 by root 2. 1 by root 2 ket 0 minus 1 by root 2 ket 1. If I give ket 1 as input, now you need not do from starting. This matrix we have already. 0, 1 you apply. 1 by root 2 ket 0 plus 1 by root 2 ket 1. Are you? So these are only 2 gates, but if more gates are there, then it is going to be more advantageous. Will have more advantage with this method, no? నార్మల్ ఓకే నెక్స్ట్ క్లాస్ నుంచి చూద్దాం రేపు నుంచి అట్లా చూడండి ఇది అయిపోద్దాం ఆల్రెడీ 3 అయింది అదే 3 అయింది కదా ఆల్రెడీ అదే ముందు ఇదైతే భలే ఉంటుంది ఓహోహో లైట్ ఆఫ్ చేయమని అవును అది ప్రాబ్లం కదా దాంట్లో రావడం వీడియో సరిగా ఉండదు
అక్కడి నుంచి కూడా ఆ లెఫ్ట్ సైడ్ పక్క
అవునా
లైట్
ఓహో
కంప్లీట్ పర్వాలేదు
ఓకే 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 escape Okay, now we go by this method 2. What is method 2? Now it is clear to you know. What is method 2? You find the unitary matrix corresponding to all operations here. So what are our operations? You should put it in reverse order. No, this is for this circuit. This circuit, what is the matrix? It will be like this. X into H. This is different circuit. No, for this X into H. We multiply that, whatever we get, same thing you got. No, for that different thing, no. This is also in, this is also unitary matrix. Product of unitary matrix is unitary. So now directly if you want to apply on ket 0, U on ket 0. U is this matrix now, ket 0 apply. Ket 1, again we need not do for H and X. So you apply U on ket 1. Okay, again 0 with 1 by 2, 1 also with 1 by 2 probability. Total probability is 1. Okay. In general, if Q is there, whatever matrix we got earlier, what is our matrix? Not for this circuit. This circuit, what is our matrix? 1 by root 2, 1 by root 2 minus, okay. Thank you. 1 by root 2 minus 1 by root 2, 1 by root 2, 1 by root 2. This is our unitary matrix. And ket 1. No, in general qubit, no. General qubit is, this is like this. Say ket psi is alpha ket 0 plus beta ket 1. Next we have H. Next we have X. Next measurement. What is the answer? This is U. This we have already calculated. What is this? This matrix form is alpha beta. You multiply simply with alpha beta. Whatever answer we get, that is the final answer. Is that okay? So now any input we can easily do this second method. Okay. Okay. Next one is, let us say we have 2 systems. So this is first system, Y is second system. Or first one, X is one task, second is another task. Order is important. This is first one, this is second one. Okay. Here the outcomes are 1, 2. Here the outcomes are A, B, C. I have two systems. First system outcome is either 1, 2. Second system outcomes are A, B, C. Now can you tell me if I view X and Y together as a single system? X is different system, Y is different system. X system possible outcomes are 1, 2. Y system possible outcomes are A, B, C. Now X comma Y, I am viewing it as a single system. First X, next Y, this is single system. Multiple system, but I am viewing it as a single system. Now you tell me what are the possibilities for this combined system. That means what are the possible states this combined system can be in. So 1A comma, 1A is one possibility, 1B is one possibility, 1C. To which is nothing but Cartesian product of these two sets, no? This set, Cartesian product, this set. But Cartesian product means order is important, no? Is that okay? Okay. So now, okay, same thing you read here. Okay. This one is sigma, the other one is gamma. This is answer is given by sigma, Cartesian product, gamma. Okay, up to this it is clear, no? Okay, this I think you may have some confusion. Okay, it will be clear in a moment. Okay, up to this is it okay? Okay. Now, okay, I'll come to this. Okay, first after explaining some operation. Okay. Now, what is the answer for this? This is first system, this is second system. What are the classical states of combined system? 1, 0. Okay, same example, different instances. That's all. Now, if I want to work on this system, my operation must be what type of matrix? Unitary matrix. But how many rows it should contain and how many columns it should contain? 6 by 6. Why? Because number of possibilities here is 6. So 6 by 6 matrix is required. In qubit Y 2 by 2 matrix, there are 2 possibilities only. That is the reason. Okay, no? If I am talking about 2 qubit system, then the corresponding matrix should contain how many possibilities? 4. 0, 1, 0, 1. 0, 1 Cartesian product 0, 1. Total 4 possibilities we get, no? If I am talking about 3 qubit system, the corresponding matrix must be. That means any quantum operation which operates on 2 qubits, like AND gate, 2 bits, no? Here 2 qubits means the matrix must be 2 by 2 or something else. No. If one quantum operation, if it takes 2 qubits as input, it requires 2 qubits as input. Then the quantum operation, what is the order of that square matrix? 2 qubits as input. See, okay, that also I'll explain. Qubit means this is my first system which is in qubit, either 0 or 1 state. This is my second system which is also in 0, 1 state. Combined system, how many possibilities are there? 0, 0, 0. These are possibilities. No, this is the order again. This is the order. In this order only, these are the possibilities. Okay, this is short form. We can also write it as 0, 0, 0, 1, 1, 0, 1, 1. Same thing, we can also write it this way. If at all my system is in this state, how do you represent it as column matrix? 1, 0, 0, 0. That means it is simply ket 0, 0. Do you agree? Like high, medium, low, off, fan. Instead of that, some other values are here. Now tell me what is ket 0, 1? 0, 1, 0, 0. What is ket10? What is ket11? Similarly, it is. Is that okay? Now, this is a 2-qubit system states or not? 2-qubit system possible outcomes. If I am talking about 2-qubit system, possibilities are I may get the answer as 0, 0 when I go for measurement, or 0, 1, or 1, 0, or 1, 1. Now you tell me any quantum operation which operates on these 2 qubits, what is the order? No. What is any quantum operation operating on this? What is the order of this? 6 by 6. You only gave answer. No. Here it should be 4 by 4 matrix. Are you not 2 by 2? Okay. 4 by 4. Why? Because 4 possibilities are there. Here, why 6 by 6? 6 possibilities are there. So this is one example. Here intentionally to show you that how many possibilities are there, the corresponding operations order is that much. Here 2-qubit system means 4 possibilities. That means square matrix should be order 4. 4 rows and 4 columns. Is that okay? Okay. Okay. Now ket11, how do you define ket11 here? What is ket11? If my classical states are like this, then don't say that wherever ket11 it should be always like this. But usually this is the notation we use. But if my classical states are like this, ket11 is becoming 1, 0, 1, 0, 0, 0, 0. Depending on the context, you should be able to understand. But most of the time, this meaning is correct. Now, is there any? See, by seeing 1, 1 anywhere, wherever you see 1, 1, this only you should not say. Here also it is 1, 1, no. But what is 1, 1? This is 1, 1, no. Now, scenario is the okay. It's not that remembering 1, 1 is 0001. Not that way. Not that way. Okay. So my intention here is to show you that how many possibilities are there, that matrix must be of that much order, and this 1, 1 confusion should not be there. Is that okay? Okay. Something we get. What is 3, 0 similarly? 000, 4 zeros, 1, 0. Whatever, some answer we get. That's okay. So here, if I multiply with this, what is answer? Here, 5th position, 1 is there. No, answer will be 5th column. That's all. No. After multiplying a column matrix where only 1 is there, 1, 1 is there, whatever be the position, 1 is there, answer will be the respective column here. So it is 1 by root 2, 1, 0, 0, 0, 1 by root 2, 0, 1 by root 2. 0 means this person. This one is this 0. This one is this 0. This is 2 ones. 2, that's why 1 by root 2 into 2, 1, no. This is again 3, 0. This is 3, 1. That's why 1 by root 2, 3, 1. Are you? Okay. Now, this is only simple naam ke vaste matrix. my intention is, what is intention here? To tell you that, that's why I asked this question. No, there are 6 elements here, 6 possible states, that if I am performing an operation on this system, that matrix must, what is the order of that matrix? 6 by 6. Qubit, it is 2 by 2. That's why that I repeated no. Why? Because there are only 2 possible states. 2 qubit system, 4 possible states. That's why 4 by 4. This is only one example. So many 6 by 6. Okay. That's so many are possible, but this is only for one example purpose I displayed. That's all. Only. Okay. Okay. 5 time. Okay. Is that okay? Okay. Okay, next one is, now we learned this thing. What is that? We have two systems, first system, second system. Combiningly, I am viewing it as a combined system, a single system. X is one system, Y is another system, but X comma Y are joined, okay, one after the other we put, and we are viewing it as a one system. We are not assuming them as two different systems. Is that okay? In that case, at least one point we have already answered. What is that? What are the classical states of this combined system? That is given by tensor product. Next question is, this system I will have some operations. This system I will have some operations. Then what is the operation for this? This is 6 by 6 wala. In general, what is the operation for this combined system? Here I am performing operation U1 say. Here I am performing operation U2. What is the operation on this combined system? How do you represent it? Two things we need. No. Cartesian product is only for sets, no. See, see, we have two systems. First system, there are some classical states. Second system, there are some classical states. Our intention is we wanted to build bigger systems by combining multiple systems. So two systems, if I combine, I will get two systems, no? X comma Y combiningly, but I view it as only one system. Then we should know, similar to X system, what are the states of this combined system XY? They are given by Cartesian product of X system with Y system. Okay, states we know, but what are the operations we can perform? First system, I know what are the operations I perform. Second system, I know what is the operation that I can perform. Based on that, can you tell me what is the combined operation on this XY system? It is, sir? No, not like that, sir. It is given by tensor product of these two matrices. Classical states are given by Cartesian product. The final matrix I have shown here 6 by 6. No, one side 2, one side 3 means 6 by 6. The corresponding matrix is given by tensor product of the two matrices. Now we try to understand what is tensor product, then we go for break. Or if you want, now only break. Break, okay. Okay, continue. Okay, after break only we'll see. New topic. No, okay, no. మెయిన్ సార్ చల్లారిపోతాయి అంటే అవును మళ్ళీ ఆడికి పోయి చేసుకొని రాలేం కదా